dominated by populations within 50 kilometers of the coastline. Take note that the Philippines is an archipelagic country, and our coastline is even longer than that of the United States. And so we really have communities living within this coastline, and this will be the source of mismanaged plastics. And these mismanaged plastics enter the waterways, yung ating mga estero, mga rivers, and transported by wind or tides. And most of these mismanaged plastics are polyethylene and polypropylene. Now, the partially degraded plastic debris, that is less than 5 millimeters in diameter, have more serious impacts, and these are what we call microplastics. These particles, these microplastics, enter the food chain through ingestion by marine wildlife, and they cause intestinal blockage in marine mammals, sea turtles, and seabirds. And this has been documented in the Philippines even. So we have whales which died, and when autopsied, would have their guts filled with plastic materials. Now, my friend Dr. Lit, a fellow professor in IBS, reported that they are already observing microplastics even in insects and in frogs. So, it's no wonder because most of these plastics are terrestrial origin. So what has been reported is in marine wildlife. But there are observations that these microplastics are also entering the food chain of the terrestrial microorganisms. Okay? Now, this is a diagram from Jambeck, the same article in Science magazine. What I am pointing out is that the data were generated in 2010, but it's now almost 2020, and we have not managed our plastics. And so it means, if even at low input, it's about 15%, and that would be about, in 2020, that will be about 50 metric tons entering. And if the middle, it will be about 100 metric tons annually entering the marine ecosystem. Okay, I will not discuss this anymore because this was explained by Dr. Del Rosario. Now, problems. Bakit ganun? Sige. Hindi, advance na yan. Okay, next slide. Okay. Not all bioplastics, as discussed by Dr. Del Rosario, are biodegradable. And I will be presenting research from UP Baguio that shows that these bioplastics that are available in the market are not really biodegradable. And this is a report from 2017 by Wei and Zimmerman, Microbial Biotechnology. The bioplastics have lower durability and lack compatibility with the existing equipment and the end-of-life management system, so that their scale of production worldwide are still limited. So, hindi rin solusyon ang biodegradable plastics na gamitin. Now, what are the important factors restricting plastic biodegradability? Hydrophobic. The very reason why we use plastics is because of this characteristic. Hindi madaling mabasa at hindi nag-absorb ng tubig. Okay? But it is also a factor why it is non-biodegradable. I'll explain why in a little while. Now, degree of crystallinity It has complex three-dimensional structure. And then surface topography. Di ba madulas yung plastic? We will explain why that will restrict biodegradation. And then, as explained by Dr. Rosario, these plastic materials are made up of long chain hydrocarbons. And that would mean they have high molecular weight. Next slide. Okay. Why are these big problems in biodegradation? The smooth surface topography, madulas ang plastic. It also means that the microorganisms cannot adhere to the surface of the plastic. Hindi makakadikit. And enzymatic degradation is a surface phenomenon. So kung hindi makakadikit ang microorganism, they cannot be degraded. So that's the one problem. Smooth surface topography, high molecular weight, and complex three-dimensional structure. Because of this crystallinity of the plastic materials, they do not have plenty of exposed surfaces on which the microorganisms can act on. Okay? And then, hydrophobic. Take note that microbial enzymes are hydrolases. They need water to be active. So the very factors that make plastic a way of life for us are also the same factors that make them non-biodegradable. Please. Okay. What are the enzymes involved in plastic degradation? Basically, these are the same enzymes that are involved in plant metabolism. Take note that lignin, cutin are biopolymers, long-chain polymers, and they are complex. And so the enzymes that will be involved in plastic degradation will be the enzymes that are involved in the degradation of lignin and cutin. And I'll explain that later. Why? But plastic materials, the polymers, are much more complex than lignin and cutin. And so they would need, it does not mean that the enzymes, the microorganisms, lignin degraders, would be able to degrade polyethylene at a fast rate because the key enzymes capable of the polymer backbone, such as cutinases, are also able to hydrolyze ester of PET and PUR. And not only that, this PE, being more complex than lignin, requires higher redox potential due to the homogeneous carbon-to-carbon backbone, which was explained also by Dr. Del Rosario. Okay, so this is a simplified version of what Dr. Del Rosario has discussed in terms of biodegradation of plastics. I have always cited my sources of information, so they're given at the bottom. Now, there must be pre-treatment of plastics before degradation. So there you have abiotic factors. That's one requirement, pre-treatment. And then the second treatment, that's why you have the scissors there, the pair of scissors, is because they have to be transformed into minute particles in order to expose more surfaces for degradation. And biodegradation will be done by microorganisms. And the first step would be biofragmentation, meaning to say that long chain of polymers have to be chopped into smaller pieces, and then you have the polymers transformed into its basic polymer unit. And this would be through the activity of the enzymes of microorganisms. And then these basic units will now be assimilated process, and that would liberate carbon dioxide, water, and different mineral elements that are components of the plastic materials. Okay? So that's the simplified version of this schematic diagram of the microbial degradation. Now, my area of study is environmental biology.
my specialization is plant and co-plant ecology. So as early as the 1990s, I already anticipated the problem of plastic pollution. So my first study was on studying the rate of decomposition of plastic. I utilized the original plastic bags, polypropylene. And what I did was to study the rate of decomposition and calculated the half-life, which was displayed by Dr. Rosario. And I found out that on the average, the thinnest, most transparent plastic bag, the half-life is 14.5 to 20 years. And when I computed the half-life, it will take 100 years for just simple
Transparent plastic bag to be completely decomposed. And that's the reason why Dr. Del Rosario insisted that the PE is non-biodegradable. Okay? Comparing this with natural substrates, my MS thesis is on the composition of leaf litter. And I found out that the half-life of leaf litter in the forest is only 0.42 years. That's equivalent to 5 months. And its complete decomposition, mineralization, will take only 12 years. Because we are talking of natural substances, and different microorganisms. Microorganisms are our natural decomposers. And they are available. So it will take only about 12 years. In comparison to plastics, which will take 100 years. Now, part of my study is to isolate microorganisms, specifically the fungi. Take note that fungi, I think, are the lignin decomposers, and I think I missed one slide wherein the different enzymes involved in plastic degradations are lignin decomposers, cutinases, and lipases. And so, the enzymes involved in plastic degradation are the same enzymes that are present in lignin degradation. And I zeroed in on fungi, first of all, because that is my area. I'm more of a mycologist. And we did this by baiting method. What is baiting method? The same plastic bags that were laid in the forest were taken in the lab and isolated the microorganisms that are growing on the surface of the plastic. I was able, and this particular fungus caused 9 milligrams loss in plastic dry weight, which is about 15% of the original weight, and with 0.5 glucose as source of carbon, but it's only after 30 days incubation. And the organism was able to produce 40 milligrams dry weight of mycelium. Next. And that's the, okay. We published our paper in 1997 Philippine Journal of Science. And this is how the plastic looks like when buried for 4 months in the soil and litter. So makikita nyo, butas-butas lang. 4 months. In 4 months, in that leaf litter, it's already about 40% degraded, mineralized. Okay, next. Okay, we identified the sterile dark mycelia, misidentified as Silaria. It's an ascomycete, and there is a profuse growth in mineral medium with optimum pH and with carbon source, using the plastic strips of carbon source. Take note that one particular requirement for plastic degradation is that the microorganism should be able to adhere to the surface. And this particular fungus produces mucilaginous sheet that enables it to adhere to the surface of the plastic. And we also subjected this to scanning electron microscopy, which showed tearing, striations, and burrowing of hypha on plastic materials. Next, please. So this paper was published in Philippine Journal of Science in 2001, and Ms. Clotario is an undergrad microbiology student. So it's a special problem. Take note the influence of having small amount of glucose in order to facilitate the organism to produce the constitutive enzymes. And this figure has very, very minimal carbon, glucose, and then plastic materials as carbon source. But if we add about 0.5% glucose, the growth is very good, and you cannot even see the plastic materials anymore. Then we have the scanning electron microscopy, which shows the burrowing of the striations in the plastic materials by scanning electron microscopy. Okay, so added pictures. Okay, next please. Then other potential plastic degraders. Basic research has very minimal funding. So I assigned this as special problem to my undergrad ecology students. Kaya ito is a series of work, and Mr. Urso used this as, I gave this as a special thesis, undergrad thesis for a microbiology ecology student. So we utilized four fungal isolates, which are all lignin decomposers, and they were isolated in stress environment. The stress environment, these are areas in Mangkayan, Benguet that have been covered with mine tailings and with very high levels of copper. We isolated those fungi because they are efficient lignin degraders and help in ecological succession in the mine tailing field. Okay? So, using molecular biology techniques, the sterile mycelia is now identified as Lasiodiplodia theobromai, Fusarium verticiculoides, Penicillium gentium, and Phycellumyces pantoni. Now, those two isolates, fungi with asterisks, are crop pathogens. Now, I have to explain why crop pathogens. They were isolated as saprophytes, no? But they are pathogens in literature. But take note that pathogens are effective because they are able to overcome defenses of plants. And take note that one of the effective enzyme in lignin plastic degradation would be cutin. And they have cutinases. And cutinases would be an enzyme that will help in degradation of plastic. But all of them are all lignin degraders. Next, please. So we were able to publish this in 2017 in Philippine Agriculturist. So what we did, now this time the substrate is polyurethane. Now the polyurethane that was used, by the way, PUR is the raw material for the formation of matrices and foams. But my student was able to get raw materials from the plastic company. And so the isolates were grown in mineral medium and using PUR, the amorphous colloidal substance, as the sole source of carbon and later as main source of carbon and nitrogen. And then this was, the degrading ability was assessed by liquid clearance assay and dry mycelial production in PUR and potentodextrose broth. Next slide, please. So these are pictures of the degradation of the PUR. So this middle one, second one is the controlled. Then you have the last and the next to the last are clearance, indicating that PUR is completely decomposed. So the more clear the tube, the lower the presence of the original PUR. And so you have there in 15 days incubation, different isolates were able to utilize all the PUR. Some would be able to utilize in 3 days, some in 6 days, others in 12 days, 9 days. But at the end of 15 days incubation, almost all the PUR were utilized. But literature says that PUR is more susceptible to microbial attack than polyethylene. Next, please. And so this would be the growth curve of the 4 isolates in mineral medium using PUL as the main source of carbon. And the lower one would be a table showing that the growth of the 4 isolates in potato dextrose broth is equal to the growth in PUR. Next, please. Okay. In Pakistan, Aspergillus tubigensis, another fungus, was isolated from open dump area, soil, and was able to degrade PU. And the enzyme involved are esterases and lipases. And there is the
This is being used also by other Filipino researchers. Next, please. So what I'm saying here is that what is being done in Pakistan, the same thing that is being done here in the Philippines. Okay. Now, researchers from UP Baguio did a study on commercial biodegradable plastic, oxy-biodegradable plastic. What Dr. Gutierrez, faculty of UP Baguio, did was to buy biodegradable plastics from SL, and the cultures that they used were taken from biotech to bacteria which are known to be cellulose decomposers, and then the well-known pyrrolate spore is a living biodegrader, and incubate that the plastic in the natural in the soil, buried in the soil, to serve as control, and the medium of analysis of the degradation with weight loss, plasticity, and static electron microscopy observation. And these are the results. Weight of loss under abnormal condition by cellulose degrader would be very different. It means cellulose degraders are not effective. And the weight loss in 30 days exposure is less than 1%. In the soil burial, it's only 1.5%. So minimal. And biodegradable plastic had higher weight loss than LDPE, but they are not significant. The differences would not be significant. Next, please. So scanning electron microscopy would show that LDPE, mas mabilis pa siyang ma-decompose or ma-degrade, 9% weight loss, as compared to the biodegradable plastic with pyrenochytic trisosporium. Okay, and the article was published in Asian Applied Sciences in 2015. Next, please. Then, the researchers from UP Manila isolated bacterial plastic degraders from Payatas dump site. And so what they did was to collect soil samples and leachate, and then incubate these for 1 week, and then the diluent were cultured in polyethylene glycol, and the assay was based on clearing of the agar, which contains the PEG, and then identify the isolates like cultural, morphological, and biochemical tests. And evaluation of plastic degrading ability would be evolution of carbon dioxide
when the bacteria were cultured in mineral medium with polyethylene glycol as a sole source of carbon. And then observation of the plastic strips in scanning electron microscopy. Next, please. So these are pictures of scanning electron microscopy. Next, please. Then we have researchers from UP Baguio that would first group, they isolated bacteria from root nodules of Baguio beans, Phaseolus vulgaris. And the isolates were tested for using high-density high-density polyethylene powder as sole source of carbon. And then again, assessment of plastic degrading ability would be loss in dry weight, observation of weight loss, and then FTIR analysis. Same as what was done in Pakistan. And then the identification will be by molecular method, the Pseudomonas fluorescens and Serratia marcescens. They cause 2% and 8.6% dry weight loss. Take note that the incubation is 90 days and the weight loss is only 2% or less than 10%. So really, the decomposition process is very slow. Next, please. Okay, so those are electron microscopy photographs showing degradation. And then the same group from UP Baguio, and this was published in the newspaper just last month. Potential bacterial plastic degraders for alkaline spring, and again utilizing LDPE plastic bag. So the same process, loss in dry weight of the LDPE, electron microscopy observation, and FTIR analysis. Next. Next, please. Next. Now, next, please. Okay, in Japan, just two more. Japan, published in Science magazine, Yoshida isolated Legionella sakayensis, and this bacterium produces two enzymes that convert PET into theriethalic acid and ethylene glycol. And then, a very recent article, courtesy of Dr. Del Rosario, showed that Austin et al., composed of about 20 researchers, the enzyme produced by Legionella was, the structure was in X-ray crystallography. PETase of the bacterium was shown, and the common feature, take note, cutinases and lipases are the enzymes that were described, and these enzymes are able to degrade semi-aromatic polyester but does not degrade aliphatic polyesters, the long chain polyesters. Enzyme is aromatic polyesterase. Next, please. Okay, so there is the article. They double mutated this organism and then researches on protein engineering, because their focus would be changing the active site of the enzymes to produce an efficient bio-based industrial polyester recycling. Next, please. So, okay, I would like to emphasize this. There's a need for pre-treatment for oxidation, and then the plastic materials have to be reduced into minute particles. Next, please. And then, studies in other countries would use UV irradiation, lactase, this is an enzyme from lignin degradation, oxidation of non-phenolic substrates, manganese peroxidase, that's also a lignin decomposing enzyme, but always there is a long incubation time required. Now, there must be identification and characterization of enzymes involved, and optimization of their catalytic reactions, and it must be a microbial community rather than just one bacterium or one fungus, it must be a microbial community of degraders. So that formation of biofilm would be very important. Okay, next please. So, where are we now in the Philippines? We have good potential plastic degraders, both bacteria and fungi. But we are only on the first step in producing an efficient technology on microbial plastic degradation. Much work needs to be done to utilize these isolated, purified, ready-to-use microorganisms. And it is emphasized that there must be pre-treatment before utilization. And so there is a need for multidisciplinary approach to research, microbiologists, environmental engineers, biochemists, organic chemists, to name a few. I mentioned that there are about 20 researchers who identified and isolated the enzymes in Canada. So, ganun ang multidisciplinary approach. But I would like to recommend the first of all, before we can do any productive and meaningful research, the procurement law, RA 891-84, must first be revised. I think that's okay. Plastic pollution is a very serious environmental problem. Science and technology can contribute immensely in providing a lasting solution. But before we can perform this task, there must be an enabling environment. And that is, RA 91-84 is the biggest challenge. And I think all of you will agree with me. Yes or no? Okay, we need to act now. Thank you very much. Sorry, I exceeded my time.
Thank you, Academician Cuevas. Our third speaker is Dr. Leslie Joy L. Diaz. She will discuss the development of industrial application of biodegradable polymer nanocomposite. Dr. Leslie Joy L. Diaz is an associate professor from the Department of Mining, Metallurgical, and Materials Engineering from UP, where she handles courses in materials engineering, material science and engineering, and environmental engineering, and mentored a number of undergraduate students in the completion of their senior undergraduate projects and graduate students for their master's and doctorate degrees in master's material science and engineering, as well as in environmental engineering. Dr. Diaz is also the environmental engineering program coordinator from 2018 to present, and the department chair from 2008 to 2014. Among her current research interests include biodegradable polymer composites, nanocomposite, rubber materials, electrospun membranes for applications in biomaterials and wastewater treatment, waste utilization in composite materials, materials processing and valorization, composite materials design, composite materials synthesis and fabrications, thermal property characterization, electron microscopy materials, degradation, and failure analysis. Ladies and gentlemen, Dr. Leslie Joy Diaz.
Thank you very much, Director Patalingho. Good afternoon, everyone. Are you still awake? Okay. So allow me to share with you the research efforts we've done in the University of the Philippines towards utilization of development of some practical applications of biodegradable plastics. To begin, let me share with you the applications of plastics in general, not biodegradable plastics, but plastics. So if you will look at the list on that side, is it showing? On that side of the slide, you can see that it's practically from what we wear to what we use on a daily basis. So essentially, it's an ubiquitous material. No? So it's something that's hard to let go because it provides us a lot of convenience. So in that case, there has to be something we need to do, and I agree with Academician Cuevas that it has to be multidisciplinary for us to be able to manage all of these issues that goes with the use of plastics. Okay, so of the different uses of plastics, you can see here from the publication of Geyer, the product lifetime distribution versus years. Okay, so this is the, it's not shown. On the y-axis, you have product lifetime distribution, and on the x-axis, you have years of the different plastics used in the different industries. So how to read this is that the curve essentially tells you the amount of plastics produced by that particular industry and how long it is used in its product life. So you will see that the blue-colored plastics for the packaging industry is the one that's highly produced in volumes essentially, but stays in the user, in the end user for a very, very short amount of time. So if we are to address plastics, I guess it should be addressing the ones used for packaging first, and then probably if we're able to address that, then all the rest can follow. Okay? So the biggest challenge right now should be on the packaging because it stays with us for a very short time and it goes now to the landfill or to other parts of dump site in uncontrolled areas. Okay? So with that said, this has been mentioned earlier by academician Dairit that there are ways by which we manage now plastic. So one is to do containment, second to do incineration and recycling. And still from the paper of Geyer, we can see that over the years, to date, we have produced 8,300 metric tons of virgin plastics and used by various industries. About 600 of these metric tons are recycled of the 8,300, but majority of that are actually discarded, that goes to landfill, to dump site, to marine environment, and elsewhere. Okay? So effectively, that's where the problem is right now. The 4,900 that is discarded. And we bear in mind that majority of that actually comes from packaging materials. Okay? So what should we do? The question now is, can we use biodegradable plastics for packaging? Because that's a major problem. And when we say biodegradable plastics, as mentioned earlier by our two previous speakers, it should be from nature and should easily goes back to nature. So effectively, the polymer is subjected by different enzymes. It undergoes depolymerization under aerobic and anaerobic conditions to produce your naturally occurring substances like carbon dioxide and water, or methane, hydrogen sulfide, carbon dioxide, and water. Okay, so that's why it's going back to nature, because these substances, the final products, are essentially present already in nature. Now, if we look at what are our options? So this is now a chart from that particular publication. And you can see here the different options that we have to produce biodegradable plastics. Okay, so actually have natural biodegradable plastics and synthetic biodegradable plastics. So even petrochem sources can produce us biodegradable plastics. So if you look at the list, there are those that are coming from polysaccharides, polypeptides, lipids, microbial polyesters, bacterial cellulose, and so on. And if we are to look at the list, I think the most abundant and most available to us are the ones in this leftmost side of the slide, which are the polysaccharides. Okay, so that's where our research in the university has been focused on. Okay, so let me start with starch. Okay, so starch, everybody knows starch. It's something that we take from cake, from cookies. So starch, it is sourced from potato, from corn, from wheat. And these are the different images. On that slide, you can see the different images that we as material scientists and engineers look at, because it gives us a structure of the material source. And from the material structure, it allows us to predict what kind of performance, what kind of behavior it will exhibit so that the properties can be predicted. Okay? So I will not go over the whole structure anymore because it might be nosebleed for many of us. So, but essentially, it shows you that starch is a crystalline and an amorphous structure. It's a combination of crystalline and amorphous structure. So what's the difference between amorphous and crystalline structure? And a crystalline structure is hard to degrade, whereas an amorphous structure is easier to degrade or easily degraded. So with the presence of certain enzymes, the enzymes will act first on the amorphous structure because it's very disordered, but the crystalline structure are more difficult to address. Okay? So with that now said, for starch, okay, so for starch, there are different types. There are type A, type B, and type C. Why do I share this with you? Because type A, type B, and type C essentially gives us a different material structure. So I'm saying it's a food product, but we're looking at it as a material source. So therefore, it has different material structures. So type A is something that you can get from cereal starches such as maize, and wheat and rice. Type B from tuber starches such as potato and sago. Type C are the ones that you get from bean and other root starches. So you can see these are the XRD profile, so X-ray diffraction profile, and this allows us to determine the microstructure, no? The arrangement of the atoms that make up our material. Further, through imaging devices, we are able to look at the morphology, no? The microstructure of the material, because the XRD just gives us signals, an indicator of the structure. So we confirm it using imaging devices. And for maize, which is an example of type A, it has a polygonal structure, and so on, you can see from the list, no? So same with the granule size distribution, it has different distribution of granule sizes, okay? So of course, the smaller it is, the easier to degrade, or the smaller it is, it will have higher number of amorphous or easily degraded number of amorphous structure, therefore it's faster to degrade. Okay? But it's not just about degradation, because this also tells us how these material sources can result to different properties. Or an example of that is the swelling power and water solubility of starch. So you can see here, there's the table of swelling power on the graph pala. The plot of the swelling power on the left, and then on the right, you can see water solubility. So with different types of starches, you have different swelling and water solubility, degrees of solubility. So as I've said, any material source, it depends on the structure of that material, okay, the property it will exhibit. Okay. So moving forward, let me now show you quickly the sum of the applications of starch. So you can see here a summary of the different applications. So many of us know, of course, the food applications of starch. So let me emphasize the industrial application, the non-food application of starch. So you can see here, the paper industry uses a lot of starch. So it's used in paper for wet end addition, size press, and surface coating. So you can imagine your bond paper will not be as white as you want it to be without application of starch. It will not be as smooth as you want it to be without the application of starch. So there is starch in your bond paper. Okay, so it provides also internal strength and surface feel depend on starch. It has improvement in the printability and writing properties. So you can see their printing paper has 4.1% starch. Industrial paper only has 1.9% starch. And then further, use of recycled paper increases the need for additional starch. So starch by itself, without processing, actually aids a lot in the processing of paper in the industry. Another application of starch will be for pharmaceutical industry. It serves as binders to sugarless sweeteners. Okay. Further, Okay. In addition to starch, as starch by itself, there are actually what we call now thermoplastic starch. So I hope some of you are familiar with this, but essentially thermoplastic starch is now working on the microstructure of starch. So remember earlier I said that starch has crystalline and amorphous structure. So what it is breaking when we want thermoplastic starch is the crystalline part, because thermoplastic starch is essentially an amorphous material. Okay? So it is processed typically using heat and pressure to completely destroy the crystalline structure. Irreversible. Destroy means it's irreversible order to disorder transition termed gelatinization. So that happens to starch to convert it to thermoplastic starch. So you can see on the left, on your right side, the native starch has the XRD profile. So once you see peaks in the XRD profile, that indicates crystallinity. But if you look at now the second two plots or profiles from the native starch, the FPTPS and the UPTPS, they have been subjected to some treatment and converted it to thermoplastic starch. And you can see that the peaks have been lessened, if not completely removed. Okay. So further, starch or thermoplastic starch are also used in these industries. In the textile industry, it is used to increase mechanical strength, frictional wear, and moisture resistance, as well as stabilizer and filler for colored inks in yarns for textiles. You also have starch for cosmetic industry. You also have starch for construction industry and manufacturing. You have starch in agriculture. So if you are employing mulching, then thermoplastic starch could be a good material for that because it just simply degrades into the soil. And then biomedical industry also makes use of starch when it is used in medical applications such as thermoplastic hydrogels for use as bone cements or drug delivery carriers when blended with cellulose acetate. Okay? So starch, which is one of the bio-sources or bio-based sources of plastic, is having a lot of applications as is right now. Huh? Further, TPS or thermoplastic starch is employed because it is highly compostable, it has high water vapor permeability, has good oxygen barrier, not electrostatically chargeable, and low thermal stability. So if you are, for example, from industry, these are the properties list that you want to know because these are the things that you want to take advantage of from thermoplastic starch. Okay. Further, let me move now to cellulose and lignocellulosic complexes. So this is where it was mentioned earlier that cellulose is one of the biodegradable plastics. So we have cellulose. We can also take hemicellulose or hemicellulose. We also have lignin and pectin, which are all sources of biodegradable plastics. Okay, so let me give emphasis in cellulose because this is what we use in our research. So cellulose compared to starch is 100% linear polymer. So kanina pinakitaan tayo ng molecular structure ng polymer ni Academician Cuevas. So kapag line lang yun, mahabang line, ang tawag natin doon linear polymer. Pero pag may mga lawit-lawit na siya na nagpapa-complex ng linear polymer na nagiging branched polymer na siya, which is more difficult to degrade. No? So highly crystalline with degree of crystallinity greater than 70% si cellulose. It is capable of intra and intermolecular hydrogen bonding. That's the power of hot cellulose. That's why it's also relatively harder to degrade, but it's still biodegradable. So it creates a tight fiber structure and it has very high or relatively high tensile strength. So you can see on that side of on your right side of the slide, the sources where the cellulose is taken from and its microstructure or the molecular structure at the bottom part. Okay. So this is also the microstructure that you will see from SEM, or the scanning electron microscope for cellulose. So you can see at letter A is a wood fiber, on letter B is microcrystalline cellulose, and letter C you have microfibrillated cellulose, and on letter D you have cellulose nanocrystals. So yung nanocrystals make up your microfibril, and then the microfibril make up your wood fiber of cellulose. Okay? So cellulose, essentially, you can see on the list, upper part of this part of the slide, left side of the slide, it is resistant to oxidizing agents. It is insoluble to most solvents. It is easily hydrolyzed by acid to water-soluble sugars. It can be modified to various forms like esters, ethers, and acetals. So cellulose essentially is modifiable. Okay? The next material I'm going to show you is chitin, which is also, or chitosan, which is also easily modifiable to convert into different types of polymers. Okay? So the different applications of cellulose right now that has been published, many of these are still in the research stage, unlike the one I've shown you earlier for starch, which are all already in the industrial application. Okay? So for biomedical engineering, cellulose have been published to serve as an antimicrobial or antiviral system. It also aids in tissue engineering. It can be a means for drug delivery or gene delivery. It can be used to serve as a biosensor by doing modification on its molecular structure. It can also serve as protein scaffold or biocatalyst. Okay, so these are just on the right side of the slide. You can see the simple processing, a schematic diagram of the processing to allow some functionalizations to attach to it and serve the functions indicated in the list. Okay. Further, cellulose can also be used for water treatment. Okay, so which are our issues nowadays. So it can be used as an adsorbent. It can be used as an additional water treatment technique, basically. So you can see also on that slide, on the right part of the slide, the mechanism or schematic diagram at which this cellulose is used as a water treatment method. Okay, so it is used in a column where certain substances are introduced containing contaminants like organic dyes, heavy metals, and then contact with cellulose will allow it to be removed from water. Further, cellulose can be used as an energy and electronics in the energy and electronics sectors in the following applications. So again, on the right side of the slide, you can see the different mechanisms or schematic diagram at which it is used. Okay? And then the other emerging applications of cellulose include enhanced oil recovery as a Pickering emulsifier, drilling fluid, personal care as an antioxidant, and in the food sector for food additive or for packaging films. Okay? So that's cellulose and its lignocellulosic complexes, which includes lignin, pectin, and hemicellulose, which I will no longer discuss. So moving forward, let me now proceed to chitin and chitosan. It has been repeatedly mentioned earlier by academician Cuevas because I think we have so much potential in coming up with this material. Okay? So chitin and chitosan, in our laboratory, we extract it from crab shell and shrimp shell. Okay? Mainly right now, we're looking at taking it from crab shell. Okay? So you can see the schematic diagram on the right side. The crab shell and then the microstructure until the molecular structure of chitin. Okay, so that's where we extracted our chitin. So as material, the biological properties of chitin are as follows. So it can serve as an analgesic. It has hemostatic properties. It is an antioxidant. It is antimicrobial. It is mucoadhesion properties. It is biodegradable. It's biocompatible. It is cholesterolemic, absorption enhancer, and low to absent toxicity. And these properties in this list of properties are basically dictated by its degree of deacetylation, distribution of acetyl groups, and molecular weight and viscosity. So it's essentially the microstructure that's present, the molecular structure that goes with chitin or chitosan. These are the list of applications. So there are so many applications that you can find for chitin and chitosan. Okay, so I will not discuss them each one, but you can see that many of them are for biomedical applications. Okay, to summarize, you have here thermoplastic starch, chitin, cellulose, and chitosan, which are the ones I've discussed or I've presented. You can see the origin and the advantages as well as the disadvantages. So on the disadvantages, you can see that what starch has high sensitivity to moisture, whereas chitin is insoluble to many solvents along with cellulose. Cellulose being crystalline has high rigidity and insolubility. And then chitosan is high water sensitivity, which are disadvantages that we would like to work on. So basically, the challenges to overcome this is to have diverse chemical functionality. They have difficult control of molar mass, microstructure, and architecture because it comes from nature. It has inadequate thermal, mechanical, optical properties as food packaging material. Okay, so basically, in order to solve this, we would like to have the following objectives. We have these objectives for our study. Establish efficient, environmental and commercially viable techniques for chemical extraction from bio-based sources, and then to establish techniques for modification, customization, and processing into a set of useful and functional polymers. So okay, let me skip this. So from here on, let me share with you some slides that will show, that will exhibit the research efforts we've done so far in the university. So our goal is to produce 100% biodegradable plastic materials from bio-based non-food resources for the packaging and biomedical industries using a process with maximized efficiency. So you can see there highlighted packaging and biomedical, because packaging, as I've mentioned earlier, is one of the major sources of the plastic problem. And biomedical, because I think we have so many doctors and nurses in the Philippines that goes abroad, so we can take advantage of them as our marketing agents, di ba? And then the material itself has very good biological properties. Okay, so to begin, these are just a reiteration of the objectives. Okay, so we have development of a biomedical device. So our focus at this point is an extracellular matrix and a wound dressing device. So what is an extracellular matrix? It is a non-cellular component present with all tissues. It acts as a scaffold. It provides conditions for cell attachment, proliferation, mitigation, and differentiation. On the other hand, you have a wound dressing. So the wound dressing must have fiber diameters between 50 to 500 nanometers, promotes hemostasis, and amenable for surface functionalization. It facilitates self-respiration, gas formation, and wound dehydration prevention, and then prevents microbial infiltration and cell ingrowth, and must have mechanical strength similar to natural skin. So these are the properties that we should achieve in order for them to be viable in these particular uses. Okay, so for this device, for the biomedical device, our emphasis comes from materials that we can get from crab shell and guess what? Banana peel. Okay, so the crab shell gives us chitin, and then the banana peel gives us cellulose. Okay, so these are some of the students who did the study. So back in 2013, one of our students did extraction from agricultural aquaculture products, byproducts, which are the crab shell, that converted that to recover or extracted chitin from that. And one of her findings is that depending on the type of fishery that you will take your crab shell from, there is difference in the amount and quality of chitin that you can get. So the XRD profile on the top part of the slide shows you that the one from aquaculture compared to the one from municipal, okay, chitin extracted material, okay, you will see that the municipal crab shell, the crab shell from municipal fisheries, have more similarity to the commercial chitin that we acquired from industry. And then again, you can see at the lower part, you can see their percent degree of the acetylation. Okay. Now, one of the students are doing extraction from banana peel. Basically, yung mga ginagamit, yung mga waste from production of banana chips. So yung peel nun, pinagkuhanan ngayon ng cellulose. So ongoing pa yung study, but we are going near to the extraction of the nanocellulose. Okay? So the chitin and nanocellulose have been put together, okay, to form your fabrication of electrospun cellulose reinforced polycaprolactone nanofibrous membrane filled with Moringa oleifera leaf powder, which is essentially malunggay powder, because we want it to have certain functionality for wound healing. Okay, so basically you can see there I forgot the term of the test, but the strips there can show you how the bacteria or the microorganism leaves when in contact with the electrospun nanofiber membrane. So this is candidate for wound dressing device, okay, or ECM. So further, the polycaprolactone earlier made use of DMAC or dimethyl acetylate solution, which is an organic solvent, which is hard, it is also a bit toxic. So therefore, we wanted to look for another solvent that is more friendly, which is acetone and acetic combination, and then did the same study, made use of polycaprolactone and chitosan. Doing the same test, we can show that there is potential for antimicrobial application. So for future plans for this, we would like to enhance functionality of polycaprolactone chitosan electrospun membrane with antibacterial fillers and chitosan cellulose with surface functionalities to enhance strength and treatment effects. Further, we want to investigate potential for controlled drug delivery system.
Into thermoplastic starch. So that starch again was converted into this thermoplastic material. And you can see that the tensile strength
On the right side of the slide. Okay. As well as you can also see the external profile. Okay. And then further, just to show you, I'll dwell on the lower part of the slide. No? So you can see expanded polystyrene. Expanded polystyrene is essentially having a lot of closed pores. That's why it's light, and it can be allowed to carry food na protected tayo from heat, no? So because it has a lot of closed pores. On the other side, you can see here expanded thermoplastic starch. So we were able to expand thermoplastic starch in the same manner that we do with polystyrene, but we're still working on the microstructure because you can see the porosity, it's not very well organized yet, okay? But we're working on it, okay? So that's expanded thermoplastic starch, okay? So, but given that, why is still starch not used as a biodegradable packaging material? I think the very critical issue there is it has very low resistance to water. So what do we do if it has low resistance to water? Okay, so our idea is to have the expanded thermoplastic starch attached with something that has less attachment to water, and we think that's chitin, but chitin is brittle, that's why we want to reinforce it with cellulose. Okay. Okay, so this is chitin cellulose polymer blend. You can see here the film from the powder that I've shown you earlier. We've made it into films like this. Okay. And then you can see the properties shown in the plots. Okay, so the one at the top is the dried. Okay, these two ones are still wet, but the one on the top is dried chitin cellulose polymer blend. And then we have also shown that the chitin cellulose polymer blend can be degraded in about 3 to 4 weeks. No? So you can see that weight loss in about 3 to 4 weeks is almost 100% already, or is 100% already. We have done the same procedure with paper. The paper took more than a month to degrade. And we all know that paper is a degradable material. Okay, so chitin cellulose material, if you will look at the list, when we compared it with commercially available packaging material, it still has very low strength, but it has good water permeability. So to improve the strength, we did incorporate nanocomposite material by adding clay material. So these are the output of the students. So you can see there the elasticity or the Young's modulus, as well as the water vapor transmission. So water vapor transmission is approaching already to that of the commercially available plastics, but we still need to work on the strength. Okay. So these are now one of the things that we need to show also, that the nanoclay reinforced chitin cellulose nanocomposite is also formable. Kasi syempre, hindi naman yan siya pwedeng plastic sheet lang, diba? It has to be into the clamshell structure. So kindly show the slide, the video please. So you can see that this is hot plate, that's on top of hot plate. So it can be formed, it can be curved. Okay, so the next slide na po. When we remove it from the hot plate and put it back into on top of the table, it removed its shape, no? Hindi siya nagstay sa shape na kung kailan siya init. This one is what we call the shape memory effect. But this is only true when it is between 40 to 60 degrees Celsius. This might be important when we use this for biomedical application, but for thermoforming activity, it has to be at higher temperatures, not lower than 60, because if you look at the CTE, the plot here on the side, when you hit after the bump here, there's a bump that you can notice. Beyond that, it no longer exhibits that kind of shape memory effect. I think I have two more slides na lang. Okay. And then next, this is the one where we have now laminated your thermoplastic starch, ETPS, expanded thermoplastic starch, with chitin. So we try to do that in the laboratory. And those are the strengths that you can see on the right side of the slide. And just to emphasize, the rightmost bar graph is the adhesion strength of commercially available laminate. So we're actually better, if not equivalent to the laminates that you actually have for food packaging materials today. Okay. So these are just our future plans, but let me go quickly to my recommendations. One is for these efforts to succeed towards industrial application really, I would like to suggest that there has to be some development of downstream processing of agriculture and aquaculture byproducts or products so that it will be more economical. And then development of manufacturing and production technologies, including development of smart machineries to allow efficient and competitive mass production. So this one, we need to work with mechanical engineers all over the country. I hope we don't just go to power plants or manufacturing plants to maintain expensive equipment, but we also develop our own equipment so that many of these processing methods we develop in the laboratory can be commercialized. And then strengthen business culture with unceasing supporting research, especially those owned by Filipino entrepreneurs. With that, I'd like to thank your attention, and hopefully I was able to impart something that you can take home.
Thank you, Dr. Diaz. That was a very informative and very interesting talk. For sure, our discussant will have a lot to say from listening to Academician Del Rosario, Academician Cuevas, and Dr. Diaz. Our discussant for the plenary session 1 is Attorney Alet C. Nunez, the Regional Policy Advisor of the No Plastic in Nature Initiative Coral Triangle Program of the World Wildlife Fund, or the WWF. As WWF's Regional Policy Advisor, Attorney Maria Aleta or Alet Cañezo Nunez works for WWF offices in the Asia and the Pacific towards the vision of having no plastic in nature through a global policy solution. Plastic smart cities and business transformation. Attorney Nunez has been working on environment and natural resources law, policy, and governance for more than 15 years now, after shifting from mainstream law practice to make our laws work a little better. Attorney Nunez is a lecturer at the UP Diliman Engineering, De La Salle University Law, UP Marine Science Institute or Tropical Marine Ecosystem Management Program, University of St. La Salle Law, Philippine Public Safety College, Master in Crisis and Disaster Risk Management Program, and the UP Law Center, doing her share both in informal and academic settings to influence hearts and minds for conservation and social justice. She graduated from UP Diliman with a bachelor's degree in political science and law from Columbia University for her Master of Law. Attorney Alet Cañezo Nunez, your discussions, please.
Thank you so much, Director Patalinihog. And thank you as well to the National Academy of Science and Technology, as well as the DOST, for inviting WWF to share some perspectives, which I will be doing for most of the time, and then also share a bit of some observations to our very esteemed scientists and academicians here. It's really good to know that for the NAST and DOST, we are looking at the serious problem of plastic pollution. Us in WWF also want to work with scientists as well as communities and governments to be able to strive for a balance between nature and people. Okay, so, and one of the things that we want to focus on really is on plastic pollution. As mentioned earlier by Academician Del Rosario, this is not just a country problem, but this is a worldwide problem. And it's a transboundary problem because all the nations are connected by oceans, of course. And if you look at it, all the plastics that we've had, half of it have only been produced the past 18 years. So there's been a 200-fold increase since plastic was invented. And as mentioned by Dr. Diaz, most of it are really focused on packaging application. And that's really also where we want to concentrate our efforts as we solve the plastic pollution problem. And then not only is there a doubling of plastic production, but 75% of that has become waste. So that's material, that's resource that has become waste over the past decade. No? And 1/3 of that has entered nature. Mostly, it's manifest in our oceans. So that's why when you talk about plastic pollution, most would also relate that to ocean pollution. Okay? And this is precisely because of waste mismanagement. Okay? In a study by Jenna Jambek, who also categorized the Philippines as one of the third most polluting, she did say that in 2015, okay, there was about 8.3 billion tons of plastic produced. So that's equivalent to 1 billion elephants. Right? So can you imagine the vast resource that's been produced? No? And then of course, yes. And because of this influx of plastic waste into nature, this has seriously damaged not only our oceans or riverways, but also our society as well as our economy. Okay? For Asia Pacific in 2006, and that only comprises 21 countries, the loss from ocean plastic pollution has been estimated to reach 1.2 billion pesos. No? And imagine for us as an archipelago, we derive so much on our coastal ecosystems as well as our coastal resources, rely so much on coastal ecotourism, and we have here precisely in Alaminos, 100 Islands. So imagine the impact to that, right? And it's not only about this waste not being managed, but current production of plastic is also expected to even rise. So it's expected to rise by 40%. So we have all these impacts that we all know of. We've seen several photos, very touching photos, especially just last month, 40 kilos of plastic waste found inside an endangered whale. No? You have entanglements, ingestion that's been studied in 270 animals, both marine mammals, birds, as well as other terrestrial. Okay. And then in terms of human ingestion, for instance, there's an initial study that for us humans, we ingest at least the equivalent of 1 credit card. We ingest plastic that is equivalent to the weight of 1 credit card. There is human ingestion, that's a fact, but what is unknown yet to science is the impacts to our human health and to our human biology. So that area still has to be studied. But the fact of ingestion through the food that we eat is there. Okay? And this impacts, especially for us in the Philippines, again, just want to highlight, because we tend to forget that we are an archipelago, and more than half of the population is in our coastal communities. Okay? So in a nutshell, right, when you talk about plastic pollution, it's not enough to just focus on the waste management. We have to also look at the upstream part. Well, how is plastic being designed? How is plastic being produced? How much of it is being produced? What is the accountability of those who produce this plastic? We say plastic is cheap, but that is not exactly true because there is some subsidy for fuel, for fossil fuel. And this also, and a portion of that, as mentioned earlier, most of our plastics right now are fossil fuel based. Okay? So when you talk about plastic pollution, talk about production as well as waste management. No, and but some lobbyists would say, "Oh, don't touch the production side because that's an economic activity. It really is a waste management issue." And this is really the lobbyists that we encountered in our work with WWF as we advocate for policy solutions. Because some would say, "You just have to focus on managing our waste and then we're good." But is that really true, right? Because even if we manage our waste, right now, for us, it's 48%, it's 84%, but plastic will continue to be exponentially produced. Okay? And even if for high-income countries, this is not enough for us to say, "Oh, they have very good management systems." It's also a question of social justice and equity because developed countries import their plastic waste to developing countries. So recently, China just closed the doors to plastic waste export. So now Malaysia and Vietnam are faced with the problems of handling plastic waste when they themselves don't have sufficient waste management infrastructure. One of the officials of Malaysia was really keen on pushing for a global agreement because they are very devastated with shipments that are falsely labeled as plastics recyclable, but are actually just plain plastic waste. Okay. So it's good that as we discussed this afternoon, we also in the coming NAS meeting and symposium, we talk about the full life cycle of the plastics so then we can address it. And this afternoon we did talk a lot on it's not working, plastic production side. Okay? That was a very excellent presentation from Dr. Diaz on what are bio-based non-food alternatives for us to come up with biodegradable packaging. I think that's a very excellent applied science work because they're very clear in terms of their objective. Solve the issue of packaging, which is the most prevalent use of single-use plastic, and also make sure that it does not compete with food consideration. Because for us, now there are biodegradable, bio-based plastics, but the issue is it uses seaweeds, it uses cassava, so then it might also lead to issues of competition with food rights. So I think that's very good, and that presentation was also very excellent because it makes use of locally available products that would have otherwise been considered as waste, right? Pag kumain tayo ng crabs, we throw it out. Sometimes we even have problems of disposing it. But if we're able to scale up the collection of these supposed agricultural food byproducts and waste, then we really are turning into a circular economy because we make use of materials as much as possible until they become so useless. So that's really locally available material, and that's the ingenuity and creativity that we should encourage in the country, especially even among engineering students from UP. And I think, as mentioned this morning, this is also where the DOST can come in and to support it through the BIS program, right? The Innovation for Business, as we scale up and commercialize this biodegradable plastic alternatives. Okay? And then also we talked about Dr. Cueva's work on fungi that would accelerate degradation of plastics. It's so striking that as early as the mid-1990s, there were already studies about what would hasten this plastic production. That's really good news, but the bad news is it's still an initial study. We want to be able to scale that up and move it forward. They already tested that in 4 months' time, there was degradation of the plastic by 40%. How long would it take to be able to fully degrade that so that it can also be used and applied for other plastic waste? And even at what scale can we use it to be able to apply that to our waste that is already there in the openly dumped areas, for instance? We did notice that in one of the study, there was fungi that were sourced from mine tailings that were also very efficient in terms of degradation. So maybe all those factors can be considered for scaling up. So again, more research needs to be done even while we were already trailblazing the way, even in the mid-1990s. And finally, with respect to the presentation of academician Del Rosario, it's really good. He went us through the chemistry of the polymers and then also distinguished for us what is biodegradable and what is the difference between bio-based plastics, right? And this is very important because we have to be able to distinguish between what is actually environment friendly and what is not. Sometimes consumer can be fooled by saying, oh, it's also biodegradable, and then I'm helping make a good choice for the environment, when in fact it can even lead to further environmental issues of microplastics when it breaks down. So it highlights for us the importance of terminology and also in terms of labeling, right? And this also highlights the role of science. It's good that we know something new, or at least we've refreshed our knowledge this afternoon, but how do we disseminate that to the general public so that they can be more discerning with their choices? How do we disseminate this so that manufacturers, packagers, plastic converters can be held more accountable and can be called out when they try to offer their plastic packaging as environmental friendly, when in fact science tells us it's not. No? So this really highlights the need for science communication. How do we make sure that all this science is communicated to all the stakeholders across the plastic cycle chain? So for us in WWF, working with other partners from the scientific community, from the local communities, with businesses, we want to be able to work together so that we eliminate plastic getting into nature. As mentioned earlier, plastic is useful, but the way we've used it has really cannibalized our world, so to speak. So we need to be able to move forward and reduce and even eliminate plastic waste. No? We can't go on in a business as usual mode. As you've seen the figures, we cannot continue to have plastic produced and plastic waste mismanaged as is. Otherwise, it will just be Smoky Mountain all over, right? Forgive me, Smoky Mountain. So we want to be able to have an ambitious target of having no plastic in nature. And we want to do this across all sectors. No? It's not just about saying no to straw, but it's also about all sectors taking accountability. Plastic is cheap and plastic is prevalent because no one is really taking the cost of plastic into nature. It's not internalized. So we want to be able to work with businesses to innovate their models, okay? To innovate their systems. And this should be transformative models. And this is also where science and technology can come in. We also want to work with a global policy platform. For us in the Philippines, we're so dependent on sachet economy, right? But how can we tell these multinationals we don't want sachets, right? But because then they'll just bring their business elsewhere. But if we're able to have this across the board globally, then all these changes can happen across the board. We have to have all these global agreements so that our efforts will not be rendered inutile by our neighboring country that does not try to manage their plastics. Okay? So that's why we're pushing for a plastic policy that will be internationally binding for all countries with reduced targets and with reporting mechanism, and where science takes a big role, okay, and including extended producer responsibility. And finally, on plastic smart cities. We have to stop the leakage in the riverways before they go into it. So just to end, there's so much room for us in science and technology to be able to address this global transboundary problem that affects not just our natural world, but also our very lives and also our economy. Science has a big role to play across all the value chain of plastic, not just in waste management, but also in production and design. And finally, there is a lot of work to be done to ensure that the science and technology is not just there in the research lab, but really turn into application, turn into public use, and turn into commercial propagation. So with that, thank you once again for this opportunity to share our perspective. Salamat po.
Thank you, Attorney Nunez. Now is the time for the open forum. But before that, I have to make an announcement for the poster committee, composed of the following: the chair, Academician Victor B. Amoroso, Academician Rafael Guerrero, Regional Director Armand Ganal, ARD Lydia Manguiat, Dr. Cynthia Rodriguez of Don Mariano Marcos Memorial State University. The posters committee meeting will be after plenary session 2. Inside the convention center near the secretariat area on my left, Copies of the abstract and scoring sheet will be given immediately after this announcement. Okay? More announcement. It's difficult to read. For us to have a concrete accomplishment on this session, National Scientist Lourdes Cruz, handling the Future Earth Philippines program, is inviting the speakers, discussants, and rapporteur of this session to join her tonight during the dinner hosted by DOST Region 1. Thank you for that. And now for the questions. For Dr. Cuevas, recognizing the potential of microbial plastic degraders, what will be its cost effectiveness if it will be developed in a larger scale? Does the process cost more than the production cost of plastics?
Thank you for the question. I cannot answer categorically what will be the cost because what we have done, the researchers in our country, what we have done is just the first step in the series of researches that have to be developed to have that technology that would convert the plastic into carbon dioxide, water, and mineral elements. I would say that there's a need for high investment in research, and possibly it may be higher than the cost of producing the plastic. But we have so much plastic waste in our country, and it's, as mentioned, it's a global phenomenon. So I cannot give the actual cost, and I would predict that it would be much higher than the cost of production. As I mentioned, in the latest article, 2018, there were about 20 researchers, top caliber researchers, who crystallized the enzyme from the bacterium and identify the active site and do biochemical mutation, protein engineering, in order to make that enzyme from the bacterium to be efficient. And that is only on one kind of plastic, that's PET. You can imagine how much would be the cost of such kind of research. So that's my only answer.
Thank you for that, Dr. Cuevas. A follow-up, another question for Dr. Cuevas from Mr. E.T. Rasco Jr. from NAST. What are the end and intermediate products of plastic degradation? Are they not harmful to plants/environment?
I cannot answer that categorically because as explained in the review, it's a long chain hydrocarbon, linear, but there are aromatic, and they have to be fragmented first into smaller units, and then you have the polymerization before you have the assimilation. So they have, even in literature, they have not been identified. I do not know if Dr. Del Rosario can help me on that.
Yes, it's a bit of a biochemical question. In answer to that, which I have to explain in somewhat chemical terms, when you depolymerize or cut the different subunits into smaller, the polymer, into smaller subunits, for example, polyvinyl chloride, the monomer there is vinyl chloride, which is very poisonous. In the same way, you have also, let's say, polystyrene. Styrene is very poisonous. So the answer to that is the intermediates of many polymers, especially fossil-based polymers, are highly toxic. So that's a good question because it doesn't mean that when you depolymerize the, let's say, the fossil-based polymers, you will solve the problem. Because if the microorganism cannot metabolize the intermediates, then you still have the problem. In fact, you just transform the problem into another type. I hope that answers the question of academician Rasco. Let me, Mr. Rapporteur, Director Patalinghood, let me make some comments which is not along this question. Can I? You see, I have been thinking that biodegradation might not be the best, if not the complete solution to our problem. We might have to use other methods like incineration or thermochemical methods plus other methods. So we have to be more, you might say,
Number three, scientific information on nutritional requirements of farm fish species and feed ingredients, and the interaction between fish and diet. Four, promote a vigorous species aquaculture. And fifth, environmental reasons for measures. In other words, social interest measures will not the non-environmental. So let us start with the key thoughts. So I'd like to turn the floor over to our next speaker. So thank you. Thank you very much for the invitation. Let us now proceed to the first speaker. Dr. Maria Quimilius will discuss the imperatives for sustainable invertebrate fisheries in northwestern Luzon. Let me read her resume. Dr. Maria Quimilius teaches marine science graduate and undergraduate courses and advises several master's and PhD students. Her laboratory conducts research on marine invertebrate ecology, reproduction, recruitment dynamics, and behavioral ecology. She has published over 60 scientific papers in high-impact international peer-reviewed journals. Aside from being a scientist, she is actively involved in marine biodiversity conservation, cultural and fisheries management of high-value marine invertebrates, stock restoration, and coastal resources management. Specialist. She serves as a resource person and advisor in national and regional technical committees related to marine sciences, policy, and sustainable development. Her research and development achievements have been recognized by various university and national awards. She served as director of UP Marine Science Institute in 2012 to 2015 and as Deputy Director of the Buliang Marine Laboratory in 2009 to 2020. She received her BS Marine Sciences and Master's Marine Biology from University of the Philippines with honors and completed a PhD in Biological Sciences at the University of Rhode Island, United States of America. Ma'am?
Magandang hapon po sa lahat. Sana sigay tayo lahat. So, first of all, I'd like to thank NAPS for giving me the opportunity to share some more findings and insights. My talk will focus on research conducted in this